Great. Thanks a lot. Okay, so I think one interesting way to sort of understand what's in a self-driving car is just to look at a little bit of the history. So if you scroll all the way back to the 80s, right? So this is an early self-driving car, and of course it's that big because it has to be. It takes all that space to fit the computing in to get it to do anything, and so computing is still a big component, right? That effort in some ways hit a real milestone in the No Hands Across America when this thing drove autonomously from Pittsburgh to LA, up to 70 miles at a time with no intervention. But from an AI point of view, this thing didn't know much, right? All it knew was it had a camera with 2 lines on it, and it was trying to keep them somewhere in the middle of its camera. So not much of an artificially intelligent agent, really. Going forward to the 2000s, so at CMU, we went off-road a little bit. And the real advance here is this is where the lidar comes in that we've been talking about. And this is where we start to get some concept of, at least in the GPS sense, where we are and where we're trying to get to. Of course, we still don't have any reasoning about objects or anything. They're just static obstacles. We just need to get around them. But nonetheless, it does pretty well. And of course, everyone's familiar with this. And the big innovation here, maybe 2 of them were good maps, the good high-fidelity 3D maps that we use for self-driving cars now. And of course, the other improvement is this thing reasons about the other vehicles. They're not just static objects. It thinks about what they're going to do. And of course, this was a real milestone in moving the self-driving car work forward. The Google Car project began around this time with this method. And of course, CMU at the same time also began to commercialize this, in this case in partnership with Caterpillar, and the key thing here was safety. And of course, everybody knows this by now. In 2015, Uber opened its lab in Pittsburgh to start working on self-driving cars. And you can see one of our early prototypes there with lots of the sensors and other things that I just talked about on that car. But we can think about, what is this? This is really going to change everything about the car. We've got more sensors, more computing, changing product specs, everything's going on. But perhaps the most interesting thing is that the system complexity is going way up. I listed some of the components there in a self-driving car. And there are more than a dozen learned models throughout these things. There was conversation earlier about, is machine learning going to be part of this solution? My take on that is, absolutely it has to. It can't work any other way. If you want to compare to an airplane is a complex system in a simple environment. A car is a simple system in a complex environment. It's not going to work without machine learning. And so the real question is, how are we going to get it to work? And that's where active optimization comes in to tune the systems automatically. Okay, so now what I'm going to do is I'm going to scroll back to professor mode here, and I'm going to teach you guys a little bit about what active optimization is. And so here we have an unknown black function there. That's that black curve. And we've got some points we've taken from this function. And we would like to optimize this thing, but collecting those points is really expensive. So we've got to choose them carefully. And so those of you that are statisticians might know this as design of experiments. Some machine learners might hear this referred to as Bayesian optimization. There are many other names for this kind of problem. But the examples we have all the time are people who do deep learning need this to tune their network architectures and their learning rates because it's expensive to train and find out how they're doing. Systems requiring physical experiments. The experiments are obviously expensive, but even in simulation, experiments become expensive. You would like to do more simulations to search parameter space than you ever have time to do. So what do? You model the function based on the points you have. We use a Gaussian process, could be anything. You then get a posterior over all the functions it might be given the information you have. And then you write down an acquisition function. This is the thing that's going to tell you which experiment to take. And so just to give you an example of one, if you take the upper confidence bound, think of the top of all those curves up there, and call that your acquisition function, that is going to prefer areas that you think they're high on the function, but also there's a lot of uncertainty about the function. So it means you'll learn something by doing an experiment there. So there's many other acquisition functions, but that's a simple one. Okay, and so then what happens? What do? You go ahead and build this model, you create this acquisition function, you find the maximum of that, which you can now do cheaply. This is just something you do on the computer, querying this easy surrogate function. Then you run that experiment and you repeat. And so let me show you what that looks like. So here's our unknown function. That gray bar, that's our current uncertainty about that function. So when we create the acquisition function, we get a straight line. So we pick one in the middle. We run the experiment. That brings our confidence in there. That makes this acquisition function. Now we can pick one on the left. That brings that in, creates this acquisition function. Now we choose the one on the right. And that continues like that. And so what you can see is that, you can see I went one slide too far. What you can see is when you get done, the right things happen. Most of the experiments were concentrated in the area that the maximum was, and yet you did explore the whole function. Okay, so professors like to show 1D curves on boards and stuff, but you might wonder whether you can actually optimize anything with this. And so it turns out, one of my colleagues, Howie Choset, has a robot snake, and it needs to climb over obstacles. And so here it is, running that exact algorithm I just showed you. And so what this snake is doing is it's searching its parameter space, trying to figure out how to climb over this obstacle. So by the way, the purpose of this snake is sort of disaster recovery, like crawl through the rubble during earthquakes. And so you often see this kind of situation. And so what we discovered here is we could get this snake to learn by using that kind of active optimization and then making the problem harder as we went till eventually it learned how to do this. And so this is just the snake practicing all on its own. And you can see by the end it's learned quite a smooth form there, and it's gotten over an obstacle that's pretty high given the size of that snake. What I'm going to do now is I'm going to skip some things. So that looks great. That algorithm, as I presented it to you, works really good on 1D when you're drawing a graph. Works okay with a half a dozen dimensions. The wheels start to fall off when you want to do like 10 or 20 and so on. So I don't have enough time to tell you about all the algorithms for going to high dimensions, but we now do 20 or even 100 dimensions. And you can look those up in my academic page if you're curious. What I want to do is scroll ahead and say, well, okay, how about using this on a car? What about this issue of you've got all these learned models in your car, they're all confusing each other because it's happening all the time and you can't figure out what's going on? My answer to that is, if you've worked on large engineering projects, nothing's changed, right? You're working in one group and someone in another group pulls the rug out from under you. They changed some spec and you didn't realize it had an impact on you. It's just that with active learning, you now have a systematic algorithm to recover from that. Okay, so what do? So we put all these learning algorithms on our cars. Those of you who read the news might know that Uber launched its self-driving service in Pittsburgh in September. And so, I apologize. I don't usually use the video here at all. I think what I'm going to do is I'm going to scroll ahead. This shows a bunch of cars driving around town. They're fine in Pittsburgh. We launched in Phoenix also. They drive there. And when you ride in the cars, what you get to see, I'm just going to scroll ahead, you get to see this on an iPad in the back of the car. So you can see here, this is using lidar, radar, and cameras, fusing them all to get this representation of all the objects around you and where they're going. So all of that is part of making the system robust enough so that we can put it on the road and actually give ordinary Uber riders rides in Pittsburgh and Phoenix. So that's what that looks like. You can see the traffic lights, some of the signs, the lanes, everything's marked in there. Scrolling ahead a little bit, I kind of mentioned this already. Again, for those of you that read the news, so we did Pittsburgh in September. December, we launched in San Francisco. Of course, that lasted about 2 days. They pulled our registrations in California. They didn't particularly like that, but we didn't care. We were fine with that. So 2 months later, we rolled out in Phoenix, and now you can get rides in Phoenix in these same cars. And of course, our return to San Francisco, we'll get back there. That's TBD when we get there. We're also transporting things, right? Uber transports things. They do food among other things, but we're getting into package delivery, and we now have a self-driving truck as well that did a nice demo in Colorado. It took 50,000 cans of Budweiser, a couple hundred miles with no one behind the wheel, as you can see there. So I think one thing to think about is how this is going to change the world. We've talked about this before. Individual car ownership, there isn't going to be a need for it anymore. It's going to be cheaper to just take a self-driving Uber everywhere. And so that will get rid of all the parking infrastructure. That will lead to the questions about public transit schemes and what are the most effective ones. Maybe the ones we have now that struggle financially aren't the right way to do. And this is our chance to, in our cities, ask what could we do with those resources instead. So just to wrap up, this is happening now. If you're in Pittsburgh, if you're in Phoenix, pull out your Uber phone, ask for a Uber X and see if you get a self-driving car. Optimization and learning are the only way this is going to work. And all of this adds up to really a once-in-a-generation, maybe a once-in-a-lifetime opportunity to reinvent our cities and how we move around, and in doing so, reinvent our lifestyles. I think it's a big opportunity. Thank you.